Okay, well, welcome everybody. It's great to start another GSNP klogW talk today. Our speaker today, as we're going to hear more from the introduction, is another APS fellow in our APS fellow series, Yamir Moreno from Zaragoza, and he will be talking shortly. I just want to introduce you the talk and also highlight our past events that you can find online. You can find the recordings. Apart from that, I would also like to say that it is February, so next month is March, and there's the March meeting happening. So, and it is supposed to happen in person, so please come to our table and say hi. We'll have our membership table for GSNP, and you can give us some feedback, have a conversation. But also, I would like to advertise our invited and focus sessions. We have many, so please join us there. And with that, also please become a member of GSNP. There are lots of benefits of membership. One of them is prizes and nominations and awards for both students and faculty, and we'll try to have more of those. The more members we have, the more of this stuff we can do. We can also have more invited sessions and focus sessions, and also completely different events that are targeted, for example, towards specific groups, especially like students or postdocs, for example, networking events, professional advice events, even immigration advice, all kinds of things that we can do for our members. But all of this requires us to have more membership so that we can move from group to division. So that is the goal. So if you can join, if you're already a member of APS, the American Physical Society, you can easily join GSNP. And if you're not a member of the APS, please join APS. If you're a member of APS, it's very easy to join GSNP. So you go to the Engage page and click on this button. So please go ahead and do that. So for today's event, I'm just going to give you a short reminder of our Zoom etiquette. So during the talk, please make sure you're on mute. Feel free to post questions in the chat box. And if they are clarification questions, one of the hosts, me or John or Shuba, who's going to join in a moment, are going to interrupt the speaker and ask. But in general, more general questions will be saved for the end in the interest of time. After the talk, you can raise your hand and the host will address you, so you can unmute yourself and ask the question directly. And if you have issues with mics or you don't want to ask the question, you can post it in the chat box and we can chat through that, and one of the hosts will ask that question and the speaker will address it. So with this, I'm gonna stop sharing and pass the mic to John, who's going to introduce Yamir Moreno.
Thank you, Daphne. Yes, it's a pleasure to introduce today Yamir Moreno, who's originally from Havana, Cuba, and did his PhD at the University of Zaragoza in Spain, worked for a few years at ICTP, and then returned to Zaragoza, where he's now a professor and director of Institute for Biocomputation and Physics of Complex Systems, a director of COSNET, Complex Systems and Network group. He has been president of the Complex Systems Society and the Network Science Society. Yamir's research has been on structure and dynamics of complex network systems, including nonlinear dynamics imposed on coupled to networks and other kinds of complex systems, multi-layer networks, and I think has had a special interest in understanding the spread of diseases both physical and I guess of ideas or social network kind on networks. And I think today's talk promises to combine elements of a lot of these. So, Yamir, it's a real pleasure. And I should say that this is also, I forgot to mention that Yamir was recently elected a fellow of the American Physical Society, nominated by GSNP, and there'll be a recognition of that as well, also at the March meeting. So it's a real pleasure, Yamir. Thanks.
Thank you very much, John, and the rest of organizers. Let me share my screen. Okay. is this now? Oops, sorry. Okay, so let me share my screen. Thank you very much, and thanks for being here, the rest of you. I was, when I was asked about giving this seminar, I was thinking on which topic I can choose. So as John just mentioned, I am sort of, attached to do complex system science. I did my PhD actually in the statistical physics of fracture processes, material fracture of materials, and earthquake dynamics, etc. But then when I moved to do the postdocs in the ICTP in Trieste, Italy, in the International Center for Theoretical Physics, I became interested in studying the structure of complex systems, and networks are the backbone of complex systems. At that time, we started to study diffusion dynamics, and in particular, disease dynamics, which we are now encapsulating in a sort of more general concept that is what we call contagion dynamics. And contagion means spreading of diseases, but it could be also behavioral contagion. It could be also diffusion of ideas, information, etc. I will try to summarize a little bit what we have been doing, or what has been doing in the field in the last 20 years. Maybe I was too optimistic when I provided the title and the abstract, and maybe I kind of run short of time by the end of the talk, and I don't have maybe too much time to talk about higher order interactions or higher order networks, which is very recent topics. But anyway, I will try to cover as much as possible. So the main object of a study is the study of disease. This is not something that is recent, that we have been studying just because now is COVID-19, because it's something that has been addressed by a lot of people, not only physicists, but applied mathematicians, computational epidemiologists, public health scientists, etc., since quite some time. The sort of models that we implement, that you will see that in the next few slides, are very simple from from the mathematical point of view, are really simple. The main problem that comes into play here is that we are modeling something that is happening normally as a result of transmission between humans. That means that is a process, is the diffusion process that is mediated by humans. When humans comes into play, this start to be really messy and really complex, because then you have a lot of different possibilities regarding the behavior of individuals, and that will, all of these difference in behavior will impact the course of the disease. It's anyway a very important topic, because as you see in this map, there have been a lot of emerging infections since in the last 20 years. Many of them you already know for sure, because you have been, for sure you have heard about SARS, about H1N1, Zika, tuberculosis, etc. There are a lot of diseases that could be modeled and have been modeled recently, in part because the network theory have started to allow to accurately reproduce the structure of the populations, on top of which the virus or the bacterium, the pathogen is propagating, but also because we have more data, and data means that we can characterize in more details the system that we are simulating. Despite all this effort, however, the prediction is of the course and unfolding of a large scale disease is still a major challenge. And the reason is precisely what I was mentioning before. The reason is that we are not modeling a hurricane in which you do a prediction. Whatever the prediction you do, the hurricane will not change the course as a result of any reaction that you might have. Of course, it can change the course because it changes the temperature or the pressure or whatever other physical process, but not because humans do something. In the case of the diseases, it's completely different. We are the carriers of the disease in most of the diseases that we are studying. In some of them, like Zika, this is also mediated by mosquito, but in general, human behavior have a huge impact in the unfolding of the disease. And this is a big problem when it comes to mathematically modeling the disease, because essentially we don't know the laws that govern human behavior when it comes to modeling reactions or behavioral adaptation to the presence of the disease. On the other hand, we don't have a sensory system that is as developed as what we have for climate or for meteorology or to weather prediction. There have been a lot of technological advance in those areas that allows you to you have almost in every big city or almost in every city, in every town, or even in the middle of nowhere, you normally have a weather station that measures temperature, pressure, humidity, etc. And this is all incorporated into the models that allows you to make those predictions. We don't have that surveillance system when it comes to measure what you need in real diseases. You will need to find incidents, the behavior of human, the network of contacts, a lot of factors that are playing a key role in the unfolding of the disease, and you don't have that sort of information. And actually, as you sure are aware, at the beginning of these pandemics, it was a little bit messy. The fact that the data was not the structure, was noisy, was incomplete. We were missing a lot of infected individuals, both in time and also geographically. Sometimes governments is not this case, but this is something that happened, for example, when the outbreak of the swine flu or the H1N1, sometimes governments kind of underreport just because that will create an aversion to go to some places. So sometimes the governments underreport the number of cases just to avoid this sort of reaction from people. So in general, this is another problem that we have. Anyway, in the last few years, we have been able to gather more and more data. And now we have GPS location of individuals, for example, that allows you to build network of interactions, and those network of interactions you can plug into your models. Essentially, the main driving the process is a process that is essentially discrete. In geographically speaking, the only difference now is that the time scale of the disease or the diffusion process is really, really fast compared to what we was 4 or 5 centuries ago. For example, this is on the left of the map, you can see the map of the propagation of the Black Death in Europe in the 14th century. It could be very accurately modeled as a continuous diffusion process for which what is the equation. You can define what are the wave and what is the front wave of the propagation, etc. And this is something that reproduce very well how the pattern of evolution of the disease was at that time, that it took 3.5 years to go from Southern Europe to the Northern Europe. Right now, it's not that easy because you don't know the constitutive law for the dynamics. This equation does not apply anymore, essentially because people take a flight and then they move. They have these long-range connections. It's not anymore propagated in a sort of a grid or a lattice that is Cartesian, let's say, space. It's more on a network of interaction that is defined essentially by connections between different places in the world. So could be a flight, it could be a train, it could be by car, there could be ships, etc. Transportation means in general are able right now to take people from one place to the other in less than 24 hours. And this is one of the examples of one process that was really very fast in propagating SARS, and the COVID-19 is the most recent example that we have, that it was reported for the first time officially the last day of 2019, so 31st of December 2019, and in March Europe was in lockdown. So in 2.5 months it was the unfolding was fast enough as to make politicians to decide that Europe have to go into lockdown in 2.5 months, while the Black Death in the 14th century, it took 3.5 years to go from the Southern Europe to the Northern Europe. So this is the problem. And this is something that we need to take into account when we model a disease propagation process. So these are the main ingredients, apart from other more, but these are the ones that you cannot miss when you want to model a disease dynamics. So first, how the disease is transmitted. So this means who is the carrier, and how these interactions happens. Then the disease stage. So normally we were used to deal with diseases that were susceptible, infected individuals, and then the sick or recovered individuals, etc. But most of the diseases that you saw in the first map have one main characteristic, and is that most of them, individuals are contagious when they are symptomatic. This is another thing that COVID-19 is tricky in that sense, because you can be contagious, you can be infectious before you develop symptoms. And actually, in many cases, you don't even develop any symptoms. So that's why also at the very beginning, a lot of measures that were adopted for other diseases failed, because like measuring temperature, etc., because people were actually infectious, but they were not showing any symptoms. So you need to know as much as biology as you can of a given disease. So this is there. Then what are the disease stage, of course, and then human behavioral change. This is also really, really important, because human is documented that humans react to the presence of the disease. And for example, you avoid meeting other people that might be infectious or not. You avoid going to places where they are maybe hot spots, where the incidence is very high, etc. Sorry. So this is also very critical, and this is where we are at loss. We don't really know accurately how to model human behavior. We can make some guesses, we can infer some behavior from data, but if you want to study analytically a given problem, you need to know, or you need to come up with an equation that allows you to model human behavior. These equations, we don't know which is, and I doubt that there is only one equation that allows you to model human behavior. Of course, you can adopt some approximation, etc., and some of them we will discuss later, but I think that this is where the big bottleneck in disease modeling is right now, and how to incorporate human behaviors. And just to show you couple of examples of what sort of data we need to incorporate. This is one of them. This is, for example, in this example, what you are seeing is each dot is an airplane. This is focusing in London, but this is air traffic. Each plane is moving from one city to another one, so it's carrying people that are potentially infectious, or potentially they are transmitting the disease to a place that is hours away from the source or the city case. So this is one of the things that we need to take into account. Fortunately, there have been data that there is data right now, not only about planes, but also about other transportation means. The other important point, as I was mentioning, is the human behavior, how humans adapt. And just to put a very simple example of how humans are really, let's say, prone to change their behavior as a function of the environment, I would like to just present one very simple experiment that was done. It has nothing to do with diseases, but I think it's very enlightening. It's an experiment that was done in the UK in the department. So where you have a room where there is a coffee or tea machine, where you go and you can prepare your coffee, your tea, and discuss with your colleague, etc. So typical room that we have in our departments. And the experiment was very simple. So participant, you can take coffee or tea at the dispenser, and this is free of charge. The only thing that you have to pay is if you put milk in the coffee or in the tea. The amount that you have to pay is fixed, but you are given the choice of deciding whether to pay or not. So what they do is that each week the money that was collected, the deposit in this the collector was collected, and the difference between each week was that in front of the dispenser they put a photo of eyes or flowers. This sort of photo. So that was in front of the dispenser, and this was like, just you see that when you were serving your coffee or your tea. And they just plotted the correlation between the image that was displayed and the amount collected. And as you can guess, humans can be fine-tuned, because actually when there are flowers, you collect more, much less than when there are eyes. And also the eyes, it depends on the intensity of the eyes. You get really high level of money collected when the eyes are like looking at you and saying, you better put some money here because I'm looking at you. This is an image. This is not a screen. This is not any that is animated. It's just fixed there. But still, we are very susceptible to this kind of input from the environment. So imagine when you are facing a disease like COVID-19, you can imagine that there is a plethora of human reactions to the presence of the disease, and that in this case, the average individual will not work. So you cannot adopt very easily sort of mean field description for the human behavior, because the average individual or the average individual behavior doesn't exist. So mathematically, what you do when you are trying to model a disease spreading is to consider essentially very simple compartmental models in which you have different compartments that corresponds to the clinical state of the individual, let's say. So if you are healthy, you are susceptible. If you are infected, and in this case, infected also means infectious, then you are in this compartment. And then the R, which is normally called recover or remove, means that you are either recover or you are diseased. In this case, what is important is that the dynamics is you don't play any active role in the dynamics. So you are in that box, and you are not anymore susceptible to catch the disease or infected people. Of course, you can do more complex things. Even for this compartment structure, you can consider that there are natural death rates, that there are natural birth rates, etc. But this is not really something that have an impact a huge impact in the dynamics of the system. The more important parameter here to characterize the disease, I guess you have heard a lot about this, is the so-called basic reproduction number, which is a number that is proportional to the transmissibility, which is essentially the rate at which individuals go from susceptible to infectious individuals, also proportional to the recovery rate, which is the probability that after some time an individual recovers. K is the number of contacts, so it's proportional to the number of contacts that you have as well, the structure of your interactions. You can also do more complex models. like, for example, the one that we are using for COVID-19, because, and sometimes, like in this case, you also have latency. So you have an exposure time. That's why you see an E here. This means that once you get you are infected, you need some time to become infectious, and this is this refractory time is what is called latency. This could go into an asymptomatic branch or a symptomatic branch. And then it has been shown that for COVID-19, both infectious symptomatic, and pre-symptomatic individuals that are in this branch, all of them can transmit the disease to susceptible individuals. And then you have, of course, another more variability between the infectious and the recovery state, which includes going to ICU, etc. But this is if you want to really go into a very detailed model of diseases. So normally, when you solve those equations in a single population, what you find is this sort of phase diagram that we call, in which you have a disease-free regime and a regime in which you have active disease or an outbreak, and this point here defines the size of the disease. So this should be R naught if you want, but essentially I don't know why I changed the notation, but this should be R0 and this should be at 1. So the critical point here is at 1. So if you are below 1, you are free from the disease. If you are above 1, there is an outbreak whose size depends on this value of R. The farther you are from the critical point, of course, the larger is the impact of the disease. Quite some years ago, the interest was in calculating this, in calculating what is the value of the critical point, or what is the value of the transmissibility that will lead to an outbreak in a structured population. This is somehow not of interest anymore, because what we are now really interested in is, okay, given that there is a disease, how can I predict the course of the disease, the evolution of the disease? So I am already assuming that the disease is there and that we are in the outbreak phase. So what I would like to predict or to model is what would be the impact of that disease. And this is where, well, this is the phase diagram. This is where the structure of the population plays a key role, because now you have to take into account that humans are not normally, they are not isolated, so you interact with others, and this is where you need to take into account the structure of population, and this is where networks comes into place. You need to characterize the network of interactions, but the network of interactions not only among your close neighbors in your, let's say, household or in your workplace, it's also the network of interactions at the community layer. So what is the likelihood that you interact with someone else that you don't even know when you move across the city, etc.? All these kind of things you have to take into account, and these things, on the other hand, depends on other networks, because the likelihood that you interact with someone else might depend, for example, on the transportation mean that you use to move from your home to your workplace. If you go by biking, then it's not likely that you interact with many people if you go with your private car as well. But if you take the metro, or if you take a bus or any public transportation mean, the likelihood that you interact with other people is higher. So that means that you have to take into account also this level of detail if you want to really accurately model what are the number of interactions that a given person might have. And for that, whatever, this depends on the sort of data that you have. Of course, if you have only data at the population level, what we normally use is what we call meta-population system, in which each node of the network is a subpopulation. So imagine that this is a city, and then cities are connected by transportation means that could be trains, could be flights, could be whatever, takes you from one city to our private cars, etc. there is a connection between these two cities if at least you have one of these connections. Within a city, if you don't have more data, you consider that the population is homogeneously mixed. That means that the likelihood that you interact with anybody in the population is the same for everyone. So there is no distinction between individuals. It's a homogeneously mixed population. The other extreme is when you really have very good data, and then you can go to a sort of agent-based modeling in which you can actually represent your system as a multi-layer system and identify each layer with a sort of activity, let's say, or a given type of interaction. For example, you can use a layer for school to model interactions at the school or education system. This has been shown to be really relevant for the disease transmission, the sort of interaction, because our interactions that are long-term, are frequent, and therefore these interactions could play a major role in disease transmission. The other important layer is the household layer. You spend most of the time with your family in your house, and this is also very important. And then if you have enough data, you can also add another layer that is the workplace layer. It's also a layer where you also spend quite some time. You interact with your teammates or your colleagues, etc. And finally, joining all these layers is what we call the community layer. The community layer is where random interactions take place. So it's where when you go to a cafeteria to take lunch or to take coffee, then you interact with someone that if I ask you what are your contacts, these people might not come to your mind because it's not a regular interaction with you. This is not someone with you regularly interact. So it's someone that you don't remember, but this is a random interaction that you have there. There are some data. This data could be both synthetic if you know the distribution of these contacts, and there are some countries in which there have been studies to measure this distribution, or it could be really, really detailed if you, for example, have the GPS location of individuals, of sample of your population. If I have time, I will present some results that we have for COVID-19, in which we built this sort of multi-layer system in which each node is an individual for which we were able to have the GPS because they were subscribed to an app that was this is an app that provides data for social good. So they were volunteering to provide the data. So we have a sample of different cities in the United States. Essentially, the work that we did was in Boston. So with that, you can reproduce you have information about the sample of your population, and then you can do some simulations with real position. So you really know if subject A and subject B interacted in the workplace or in the household or in the school layer, or if they interacted somewhere in the grocery or whatever. So in general, to how we have developed this field, and I will now enter into more details, is that at the very beginning, we were working with very simple layers. These single networks that was characterizing which each node is an individual, there is a connection if there is an interactions, and we were studying different dynamical processes, of course, including spreading processes. However, this was till maybe 2011, 2012 is most of the activity of in the field of networks was in these areas, starting this sort of problem. However, and this refers to these sort of networks that are single layer, we call single layer networks, in which there is one node and one interactions between the nodes. So is a pairwise interactions, and nodes are a single entity, and there is only one layer. So you have in biology protein-protein interaction networks, you have food webs, you have social networks in which people interact because they, for example, co-authorship networks or patents or whatever. This is a communication network. This is at the internet and autonomous system level, etc. you also have some data that could be very relevant to model disease dynamics, like, for example, what is the probability that someone in the population have a given number of sexual partners per year in the whole lifetime. And this is particularly important when it comes to modeling the spreading of sexually transmitted diseases. And this is something that is also available, etc. And of course, you have data about transportation means. Here, it's just to highlight that it's important also to distinguish that not all the distribution of the number of contacts or the number of links from one node to the neighbors not only depends, depends also on this kind of transportation mean that you are representing. For example, if you represent the network of highways in the United States, you see that this is a sort of Poisson distribution because there is a geographical constraint. You cannot have 100 highways going out of a city, while you can have 100 connection with other cities if the connections is by flight. So in this case, what you get is a power law distribution, and if this, in this case, is a Poisson distribution. So you have to know which is the transportation mean that you are using in order to accurately represent the system, because the fact that you are using transportation networks without specifying anymore doesn't allow you to disentangle what is the interactions that are, if it is a heterogeneous network or if it is a more homogeneous one, etc. From 2011 or 2012, we realized that this is a way that is more accurate to represent the structure of the population, that assuming that the population is homogeneously mixing. But that with the data that we have, we could do more. We were actually saying, okay, this is my interactions, but actually interactions, as I mentioned when we discussed this agent-based model, take place by layers. So you normally this single layer network represents the projection of many different kinds of interactions. And this is what we call multi-layer networks. What we call multi-layer networks is a network of networks, is a network in which each layer is identified with a given category or with a given, social network, for example, etc. And then what you need to work with all this, with this object instead of with the projection of this source. And I will explain why this is relevant in the next slide. For example, in biology, you have protein-protein interaction network, and this is a typical graph that you see in biology, where you see that the nodes could be genes or proteins, and interactions means that there is some interactions between the elements of your system because a gene was expressed under a given condition. However, when you represent this, you are considering that these interactions are always present, and this is not the case, because if you actually think about disentangling these interactions and saying, okay, let me represent the network under hypoxia conditions, or when there is a starvation, or when there is oxidative stress, what you see is a completely different network. So this one is the addition of all these, but each of these you can represent as a different layer on the multi-layer system. The gene is the same, the protein is the same, but sometimes you have a connection here, for example, with this neighbor, and sometimes you don't have because they don't express concurrently. So in that sense, there is no link when, for example, is oxidative stress, while you can have the link under hypoxia because they both are expressed at the same time. So in that sense, this network is obtained as a result of projecting in this direction all these layers here. But if you want to model the biological process by which this hypoxia happens, you can't work with this because you are introducing spurious links in your representation. You have to work with the network that really represent interactions under a given condition. The same happens, for example, in ecology, where you have example of multi-layer network when you have mutualistic networks in which you have one species here that could be plant, for example, that are pollinated by pollinators, and there are a lot of species that are pollinator, and you have interactions between them. This can be translated into a multi-layer network in which, in this case, what you project here are the interactions intra-guile, so interspecific competition between the animals or plants for a given source. And finally, also in multi-layer networks in transportation, you have to take into account that if you want to go from A to B, you have many different ways to go from A to B. So for example, if you are studying how efficient is a transportation system, it's important to distinguish between different transportation means, because they imply different times to connect, to travel from one point to another one. So you cannot go only and do the projection of this and say, okay, I go from A to B. Maybe going from A to B implies that you do some path in A, in layer 3, for example, then you jump to another layer because you take a bus to go downtown, maybe, or to go to, you know, suburb of your city, and then you take there the metro to go downtown. So you took two transportation means, and this is something that you have to take into account when, for example, you are going to model disruptions in your system. It's not the same to assume that you will, I mean, if the disruption is the metro, people start moving to the other layers, and then this gets congested, etc. So it's a cascading effect, and this is something that you cannot capture if you are modeling the system with all aggregated information. And finally, in social networks, of course, this is another very clear example. You cannot say that you have, you know, 100 contacts regardless of where they are, because, for example, these contacts, if we are talking about online social networks, can come from Facebook interactions, Twitter interactions, or LinkedIn ID interactions, etc. And all of these interactions are different because you normally don't share the same kind of information in each of these networks. So if you want to study diffusion dynamics, you need to know the sort of information, what is the preferred network that you use to connect. Sometimes you take a piece of information that you saw in Facebook and you move to Twitter and you know, post it in Twitter or do a forward to LinkedIn ID, etc. So you need to know how information travels, because that will impact the result of your study. So in general, this is how we model this system. So with what we call a multi-layer system, that essentially is a networks of networks. So they are networks that are different layers that are, each layer have a degree distribution, so a connection pattern or a given network of contacts, and then you have connections between the layers. Normally, so here in these matrices is where the information for the interaction within the layers is contained, and then the off-diagonal blocks contain information about the interaction between the layers, between these layers. So this is a very simple example, and this is what we call supra-adjacency matrix, because the adjacency matrix of a single layer would be this one. So supra-adjacency matrix, just to say that this is a collection of networks and a collection of adjacency matrices. In the context of disease dynamics, this is very important because there are some examples of diseases that you need to model using multi-layer system. And one very clear example of this is when you have more than one disease in your system that are interacting, more than one diseases that are concurrent in your system. For example, let's suppose that you have a system of 3 diseases, that each of these diseases has its own transmission path. So essentially, the network of contacts could be different in each of these layers. It's not the same. The host population is the same, but the network of contacts shouldn't necessarily be the same. One clear example of this case is the co-occurrence of tuberculosis and HIV. Tuberculosis is an airborne disease. So you will expect that the network of interaction describing transmission of tuberculosis is the normal network of interactions that we see, for example, for COVID or for whatever. So it's a network of interaction that is characterized by your contacts at work, your contacts at the school or the community, and at home, of course. While HIV is a sexually transmitted disease, so this is a very specific network because it only means that you have to take into account your contacts with your partners, with your sexual partners. No matter, the other contacts doesn't matter because it's a sexually transmitted disease. So in this case, you will have one disease that is tuberculosis that have a network of contact that is completely different to the second layer, that is the disease characterized by sexual contact patterns. And you see that this is very relevant because these two diseases are really coupled together. This is a map to the left. You can see a map of 1990 when there was no HIV, and you can see the incidence of tuberculosis per 100,000 individuals in the population. So you see that here in South Africa, the incidence was around 200, 300, and it was a little bit more here, but here was not really high. Then in 2005, only 15 years later, you see that here the incidence of the tuberculosis is really, really high, and it's perfectly correlated with the incidence of the HIV, which you can see in the percentage here indicated. So actually, the TB, what happens here is that tuberculosis is a disease that you normally don't get sick if your immune system is strong enough. When you are infected, you don't develop the disease. Your immune system is able to trap the pathogen, so it gets encapsulated. And then it is not free flow on the blood, so it gets encapsulated, and it could remain encapsulated for your lifetime. The problem with the HIV is that, as you know, the immune system is suppressed, and then you have an immunosuppression episode, and then that means that this capsule is broken, and then the pathogen of tuberculosis is released. It goes into the blood, and then you develop the tuberculosis, the disease. And this is what happens when you get the HIV. The same happens if you are HIV positive. You are more susceptible to catch also other diseases, including tuberculosis. So this is why you need to take into account these two layers. Just to provide a little bit more of detail, let me just put in the last few minutes some example of how we model this mathematically. And for that, let's use as an example social contagion process that could model, social movement, belief adoption, viral spreading, information dissemination, etc. And let's suppose that we have a system that is a multi-layer system that is characterized by different layers, different online social networks corresponding to different online social networks, for example, Facebook, Twitter, LinkedIn, and each of them is characterized by a contact, by a pattern of interaction. So let's first choose the model. The model that we will going to use is very simple. Is a model that has been used for disease dynamics, but also for information dissemination, and it's a susceptible, infective, susceptible model, SIS. So with probability beta, you go from susceptible to infected individual if you are in contact with an infectious individual, and after some time you recover and go back to the susceptible state. The dynamics for a single layer network in terms of a microscopic microbial approximation, is very simple. So this is the probability that at time t+1 node I is active, or in this case is infected. This depends on the probability that you get in touch with someone that is infectious, this PJ, among your neighbors. So this is the interaction, the adjacency matrix, the matrix that determines how likely it is that you get in touch with someone else. This is the transmission probability, and then this is the probability that you don't get the infection by any of your neighbors. So this is there. So, and this is the matrix that characterize the contact patterns. Essentially, we imagine this process as, imagine that you have here, this is the focus, and then imagine that you are sending random walks, or if you want, piece of information from one node to the other ones. So the probability that the one piece of information goes through this link is 1 over the number of neighbors that you have. If you send exactly the number of neighbors that you have, you expect that on average, each of them are contacted, each of them are reached by your piece of information. So this is what is reflected here. So this is essentially, this is the density matrix that's it's 1 or 0, 0 if there is no connection between I and J, 1 if there is connection between I and J. So 1 over K is the probability that if you send one piece of information, it gets it gets to you. And this is to a power of lambda, because this is just to say, to take into account the fact that you can send a lot of pieces of information, not only one, a lot of pieces of information. So when this is really infinite, when you send an infinite number of pieces of information, this matrix here is exactly the same as here. So it's the density matrix of your system. So this is for single layer networks, and you can work out this and reduce this to a fixed point equation, because you can get rid of time, because there is a steady state in your dynamics. And then you find that the critical point depends on the largest eigenvalue of this matrix here. And this is the relation between them. So essentially, the critical property of your dynamics depends on the largest value of a matrix that characterizes the structure of the system. And this is where the interplay between the structure and dynamics is important, because you know that this matrix here can be changed if you change this parameter here. This is fixed because this is the topology, and you assume that the topology is fixed, the network is static. But what you can change is this dynamics, that essentially is the number of pack rates or the number of times that you send a piece of information through your neighbors at random. So this is for single layer networks, and this is a very a result that was now since I don't know, early stage of network epidemiology 20 years ago. And now let's do it for networks that are multi-layer networks, in which you have more than one layer. So instead of having the adjacency matrix that we have before, what we have is this supra-adjacency matrix that essentially in the diagonal blocks includes the connections within the layers, and the off-diagonal blocks account for the connections between the layers. The equation describing the dynamics is the same. The only difference is that now it's not only a node, but is a vector in this case, and then you build the same matrix that you have before, but in terms of the supra-adjacency matrix. So in this case, is the probability that a given node sends some piece of information using a layer alpha. So this layer, this new index refers to the layer. So this is node I in layer alpha. So in Twitter or in Facebook or whatever. So this means essentially that you are sending your piece of information through layer alpha. And what we want to try to understand is what new results you get from here. Again, you can adopt some approximations, you can solve it, and you find this sort of eigenvalue equation. And what you obtain is, again, that the critical point of your dynamics depends on the largest eigenvalue of the supra-adjacency matrix. So not of the single layer matrix, but of this supra-adjacency matrix that you find here. So this one here. There is possible to find approximation for this, and actually you can do a perturbative analysis, and you find that at first order, the largest eigenvalue of the supra-adjacency matrix is equal to the largest eigenvalue of individual matrices in your system. So this is what you get at first order. So that means that there is one dominant layer. There is one layer, even if your system have n layers, there is one that dominates the dynamics of your system, and it is the one with the largest n value. This is the one that determines the critical properties of the whole system. And this is really interesting because that means that even if you have different layers and you have diffusion dynamics occurring on top of different layers, there is only one that is really of interest, because this is the one that determines the critical property of your system, and is the one whose structure gives as a result the largest values among all the layers in your system. This is what we call the dominant layer. These are just numerical simulations just to play a little bit with different configuration of the networks and different parameterization. Another interesting aspect of this is that the fact that this depends on this parameter here, it implies that if you change this in one layer, because this depends on the layer, this layer might have not been the dominant layer before, but as a result of increasing the activity of the layer, it could be the new dominant layer. For example, this is the case that is illustrated here. Up to this point, the dominant layer was layer number 1, but it was there for lambda equal to 10.0. So this is the largest in value for lambda 1 equal to 10.0. This is layer 1. And then layer 2 start to increase the activity. At some point, there is a crossover. And for lambda larger than 20 or 30, actually, this is 32. You see that the dominant layer now is lambda, is the second layer, not the first one. And actually, this is what you see here. From this point on, the dominant layer start to be the second layer, not the first one, just because the activity here was increased. So this is really interesting. It's a phenomenon that is inherent to the fact that your system is a multi-layer system. So just to conclude in 1 minute, just to, I wouldn't have time to discuss a higher order system, perhaps in another occasion. Let me just mention what we did with this data that I was mentioning. It's again a multi-layer system, and in this case, we have enough data. All what we have been discussed previously regarding this Markovian approximation is a synthetic network, so it's theory, etc., without no data. But when you have data, you can actually go into detailed numerical simulation. Of course, here you don't have the equations that characterize the whole system, because all the nodes are different, but you can do numerical simulations and simulate different scenarios. This is what we did in Boston. For the Boston area, we have enough data that allowed to build a synthetic population that in which you know where the people were located at each time step, and then you also implement this compartmental model, and then you are able to simulate different situations. This is what we have, the baseline that we have, because we have data of January and February, so without any lockdown, without any change in human behavior, and we have the number of contacts in each of the layers that I was mentioning before. So what you can simulate is medium closure, for example. That means that you close the schools and you reduce the interactions in the community layer by closing mass gathering events like big sport events or churches or restaurants, etc. And then the non-essential closure that was followed by by this, and you see that the distribution of contacts drops abruptly and in a very important way. So here the average number of contacts is around 60. Here it was around 20, and here it's only 7 or 8 contacts. With this, you can model scenarios, and the scenarios means what happens if. What if a scenario? This is if you don't do anything, and you see that there is a big peak and there is 75 attack rate. So that means that 75% of your population will get infection. And of course, this is translated into a lot of deaths, because you cannot, the healthcare system is it cannot handle this level of infection. And then the other two scenarios is the one in which you have medium closure and the one in which you have non-essential closure. So even if you have non-essential closure in both, we simulated a scenario in which the question was, well, what is the level of contact tracing that I need and quarantine that I need for this to contain the disease. So for the healthcare system to be able to manage this level of infection. The answer is you have to go up to between 20–40% of contact tracing and quarantine all those that are susceptible and the immediate contacts at home, close contacts. So this is the answer. I will not enter today because I don't have time, but you can see here the projection. If you don't do really contact tracing, you will have another peak here that is really big. And this is because there is one aspect of disease modeling that is really, really important to understand. Disease disappear not because of the lack of infectious, but because of the lack of susceptible. If you close in false, let's say, in the sense that you close and then when you open, there is still one or a few infections going around, sooner or later you will have another peak because you have still enough susceptible in the population. If you build immunity, then you are somehow safe because then immunity protects you from getting the infection. And that's the effect of vaccine and other measures. So this was what we did. And as you can see that under the CS scenario, where you have contact tracing 40% efficient and detection 50% efficient, you can see that you can handle that because you are, this is the dark blue, you are always below the maximum level of ICU beds in the hospital. These are real data of hospital in the Boston area. So this level is real. And this is the level that you will predict in this scenario. So I think I will stop here. I'm sorry because I don't have time to discuss the higher order part of the talk, but I think this is enough. I don't want to be, to take too much time of your. Thank you very much.
Thank you, Yamir. Applause for everybody. That was really interesting, and we have time for questions. You can either ask in the chat or unmute yourself and as well. Actually, I just to get started, I was curious. You mentioned briefly sort of things that one can do to sort of control spreading and so forth, and I was wondering if you thought about that not only for diseases and so forth, but also for opinion dynamics and with all the spread of fake news and things going on, if there's things that one can do about changing the structure or connectivity that can alter spread of.
Yeah, this is very interesting. Although it's probably harder to do because whenever you have humans into the equation, things start to be really complicated because you cannot anticipate all sort of behaviors or human reactions, etc. But essentially, yes, there are a few techniques that have been explored using essentially also methods from disease or from network epidemiology. The idea is to immunize nodes so that they are not they don't become the spreaders of information that you don't want them to spread. And there are some studies that you can do immunization in many different ways. You can target the highly connected nodes. You can target those that have different centrality characteristics, etc. More recently, one thing that have been explored is to use the use of counter information, let's say. So you once you detect that there is a diffusion process going in your network, you kind of launch another diffusion process that try to kill that one. And for that, for example, people are using now these multi-layer networks, so in which you try to shortcut the spreading of fake news or misinformation using the own networks to spread faster the good news or the news that are for real. This is really something that is in the making because we just started to study how to identify those nodes that are susceptible of spreading misinformation, etc. And many of these methods depends on our ability to detect those nodes. So it's not easy to implement or to have an algorithm or something that you really can recommend to policymakers or those that have to implement those sort of algorithms and response.
I see. No, that's really interesting. And here in Canada, of course, we just lived through this whole episode of a protest that really was amplified by social networks and so on, and took a life of its own because of that.
Yeah, related to that also, especially for, well, it was something that was studied before, but I think it's now more timely, maybe highly topical right now, is to study the interactions between information dissemination and disease dynamics, precisely because humans change their behavior as a function of what they see, what they hear, what they read. You need to combine both things. Diffusion of information and diffusion of the pathogen or the disease itself. And the difficulty here is that even if you model these two processes in a similar way, the time scale is completely different. So here the problem is how to accurately take into account the differences in the time scale of the propagation processes. What is the proper, ratio between one and the other, and these kind of things. And for that, we need data, and data is not always easy to find for privacy reasons, but also precisely because once you know this is happening, you lost the data. You are not able to go back in time and start measuring what happens. So you normally miss the very early stage that are critical for the characterization of these dynamics. There is one that have a political question. Yeah, go ahead. If it is too political, I'm
yes,
go ahead.
Hi, I'm Tim Slukin, and I'm in Britain, and there have been politicians here who have said that the mathematical modelers are useless, they said, and they have produced all sorts of studies, which I think are probably cherry-picked, which from economists and so on, saying, look, these mathematical modelers are failures. And so that's my first question. And my second question, I guess, is concerned with your previous comment, which is to do with the diffusion of information, because it's clear that people do avoid crowded places when they know that there's an epidemic. And, even Galileo in 1610, when was hiding from the epidemic in Florence. But there's a real question as to whether, if you like, one should hide from the epidemic voluntarily, which is what the typical right-wing response in the Western world is to say, leave this to the common sense of individuals. And the typical left-wing response is to say, we need a government response, we need some guidance from the government to tell us what to do. And we surely need some modeling that tells us how much the use of common sense, if you like, competes with the use, for example, of, there are typically, turns out that big business, for example, has wanted to keep the state open, has been very discouraging about closing of businesses. And in fact, of course, information about the 1918 Spanish flu, so-called Spanish flu epidemic, was suppressed in Britain, certainly, precisely in order, because they knew that if the information traveled, that people would try and isolate and they would not go to work and they might not fight in the war and various things like that. And I just wondered whether you had any comment on any of these issues.
Thank you very much. Very interesting question. So regarding the first, I would say that mathematical models are really not perfect, but they are very, very helpful if they are used correctly. So essentially what we are able to do now it's what if scenarios. So you can do what if scenarios. You can do what happens if I do nothing, what happens if I do this, what happens if I do that. And provided that the politician or whoever is making a decision knows that this should work. This is a mathematical model that works. It has been shown that we are able to reproduce some dynamics and also to compute quantities that were hidden for us at the beginning. So when, for example, when at the beginning of this pandemic, the network epidemiology and computational epidemiology, mathematical modeling, showed that we were missing a lot of infectious individuals. This came, the very first time, this came from mathematical model. The mathematical model told politicians and healthcare and public health administrators, you are missing something because the numbers don't add up. If we reproduce the models with these conditions, it's impossible that you can have only 100 individuals that are infected. Something is happening here, and this is so mathematical models suggested the fact that 90% of the first infectious individuals were gone unnoticed, and this was a result of mathematical modeling of evaluation of the scenarios. Of course, we are dealing with a system that is adaptive dynamics. So when you make a prediction and you tell people this is going to happen, people adapt their behavior, and then your prediction failed as a result of that adaptation. But this is not because your model is wrong. It's just something that your very same model can predict. My model tells you that if you do this, you will get this. Of course, if you change what you do, then you will not get to that point. You will get to another thing. This is what mathematics and the modeling can tell you. I agree anyway that there are a lot of noise in the system, in the sense that there are a lot of colleagues that I'm sure with good intentions, they from one day to another started to make predictions using models that are not as easily interpretable as they may thought and may think, and then it's a communication problem as well. So sometimes it's not a problem of the model, but the problem of who is communicating the result of the model. This on one hand, this is my take on that. On the other question that you make is I agree that I think that there should be a mix of measures. There should be very simple measures that should be enforced by the government or the public health officials, and there are other measures that works if individuals adopt those measures, because sometimes one thing is to recommend and one thing is to impose. Here in Europe, I was surprised, to be honest, that people were, at the very beginning, they were scared. So they were actually accepting all lockdown. We were into a very strict lockdown for a couple of months, and then we exit that lockdown slowly. So from March to June, mid-June, we were really with very strict mobility restrictions. Then there is this fatigue that then people, do not accept the same kind of measure. They don't accept with the same sympathy that they were accepting at the very beginning. So I think that there is a mix of things. Again, it's a communication problem. I think that people are prone to accept what you suggest if you explain why, and if you explain it very as best as you can. The problem is that, again, here there have been, even in my country, in Spain, here the healthcare system is organized in a way that those that can legally impose these conditions are the autonomous community, not the central government. The central government can only do that if they declare the state of alarm, which is something that is really when you have a huge problem. So at the very beginning, then once the state of alarm is not active anymore, this is the responsibility goes down to the communities, to the sort of states, if we were talking about United States. So where you have a president of the community that is the political responsible of adopting any decision. And here in Spain, there was a mix and a mess of measure. Here, there. There was also the legislation that they were going to the court to decide whether the measure could be adopted or not, etc. And this, I think, undermines people's trust, and that's also a huge problem that we have. But I will say that, scientifically speaking, there are some measures that works that can be adopted by a government, and there are other measures that are left to the people and should be adopted by them. So I don't have strong position in any way. I think that the two extremes are bad. So you cannot leave everything to citizens, and you cannot ask the government to do everything. There should be something in between.
I
don't know if
my email, if I may.
Yeah, okay. I'll be happy.
Thank you very much.
You're welcome.
Yeah, thank you. Are there other questions? I actually, I mean, just arising out of that conversation, you mentioned that one can make projections and then people's behavior alters and then it's no longer valid. But can you put that kind of adaptation, or have you tried putting that kind of adaptation into the modeling itself, saying that the rules of behavior might be influenced by the general state of the network? So if there's fear or something, people would shift into one mode and another.
Yes, you can do it, but the problem is that it happens like in the weather forecast. What you get is the most likely outcome, and then you have uncertainty. That is a con that it opens up very, very fast. The best prediction that you can do normally have a validity in time of 1 at most 2 weeks. More than 2 weeks in advance is really, the confidence interval are really huge in your prediction.
Right.
And while people normally, people do not question the fact that you see in the news, tomorrow with a likelihood of 80%, there will be rain. And then there is no rain at the other day. People doesn't question the validity of that prediction. They say, oh, okay, this is 80%. I'm used to that. It might happen. It's likely that it happened, but it might not happen. When it comes to the disease, they don't think in the same terms. They think that your prediction should be 100% sure. That is binary, is this or that. They don't think in terms of probability, in terms of uncertainty. They don't recognize that your prediction always have some degree of uncertainty. And that's why they get confused and they say, oh, this is wrong, because I see that instead of having 500 people per 100,000 infected individuals, I have 700 or I have only 200. So this is where they think that the prediction fails. But
that's absolutely right. And even in weather, you might be over optimistic. In the other scenario where it's 20% chance of rain and it rains, people complain.
yeah. Well, they complain, but they are not equipped with this sort of thinking. So in principle you can do, but it's always very hard to measure because we don't have the possibility or we have very low capabilities of measuring real-time dynamics on disease, because you will need to measure a lot of things to be sure that you are modeling it correctly. So normally what you do is a scenario evaluation. You say, okay, let's suppose that this measure, for example, imposing the social distance, 2 meters. So let's suppose that you have, from 30 to 70% adoption of these SIMs in the population, and that if you adopt it, that will reduce the probability of transmission by 50%. or by 40 or by 10. So at the end of the day, you have a lot of different combination of all this parameterization, and all of these produce a given forecast. And then what you normally use is the worst case scenario, not all those scenarios. Say, okay, in the worst case scenario, that only 30% of the population adopt this, and that this reduce only by 70% the transmission, this is what I will get as a number of infectives per day. And this number of infectives per day will imply that my healthcare system will be overloaded. So I have to do something else. At the end of the day, maybe the worst case scenario was not what happens. It was in a middle scenario. And then maybe you didn't have to do that, but you have to always place yourself in the worst case scenario.
Yamir, I had a quick.
Sorry.
I was wondering, I mean, based on this discussion we've been having, if in your multi-layer modeling, can you look at the effects of, say, putting in a mix of, so you have your disease parameters that and your networks that determine some of those layers. But what if you had an information layer too? So some way to spread information coupled with these other, things that are related more directly to the disease. Would that make it?
Yeah, theoretically, we have been exploring, we and other people also, not only us, we have been exploring the interplay between a diffusion of information and diffusion of disease dynamics. Numerically, you can also do, if you have an agent-based modeling, essentially you can do whatever you want in agent-based modeling, because if you have good data. The problem is always the same, is that you have to guess the human behavior. You have very little evidence of how people react to a given situation, how people consume information. And in this case, it's really important because there is a lot of heterogeneity. So it's not only, it's not only, enough to know that maybe 30% of the people will be affected by this piece of information. You need to know who are they. You need to know if they are those that take the tram and interact with the other ones, or if they are people that have middle income that can do smart working and they can remain home, etc. So sometimes you need to know not only the percentage of the population that would adopt a given measure, but who are they. This is where the tricky part is. But in principle, synthetically and theoretically speaking, you can model that, and there is the mathematics to model that is developed. So it's not fully solved, of course, because you always end up doing some assumptions, but it's in principle you can extract some meaningful insights.
Thanks. Tim, you had another comment?
Yes. I guess one of my comments. Yes, if we'd been looking at an outbreak of smallpox or Ebola rather than an outbreak of COVID-19, then presumably we would have had much greater conformity with the rules than we've actually got. And that one of the problems with the COVID-19 is that it's prejudiced against elderly people and people who are sick. And so there's a public goods game involved here, or a sort of dilemma problem. And as soon as it was realized that, in fact, there's a difference between your own benefits and the benefit of society as a whole, there was a strong temptation to cheat. Right? Yeah. And that has never quite been addressed properly. I mean, it's difficult to address in the models. I mean, and it's difficult to address for the community as a whole. And it's one of the reasons why people on the left are very suspicious about leaving it to individuals' common sense. Because if you are young and healthy, then indeed your local optimum is to take no notice. Right. Whereas it wouldn't be if, for example, it was an outbreak of the plague, or as in Galileo's case, for example, then or an outbreak of cholera or something like that, then there wouldn't be this this strong strong moral hazard element. And I'm not sure that
no, I agree.
Deal with all of this. I mean, it's a political science question as much as a mathematical question.
Yeah, no, but I agree with you that it depends a lot on the disease as well. There have been some work modeling, introducing this sort of game theory into coupled to disease dynamics, but not for this sort of disease. It's more to model vaccination adoption. So it's more for not for this, for other kind of measures, but for vaccination. It's what there are some works of people that have mathematical epidemiologists that have done some modeling in that direction. But yeah, I agree with you. There are some other diseases in which guessing the human behavior or that the human behavior is not really fundamental. For example, Zika. Zika is a disease that you can model very precisely because humans normally doesn't change the behavior because it's not so it's transmitted by the mosquito. There, the key is to reproduce the population of mosquito, and this is something that you can do using artificial intelligence methods. And there have been some teams that have done very precise modeling of Zika. So yeah, I agree with you that depends on the disease.
But presumably, although it wouldn't be very helpful for this particular epidemic, it would never be worthwhile trying to make models in which these kinds of dilemmas existed to try and see what kind of results one got and what were typically the difference between predictions and whether things were compulsory or not, and all sorts of stuff once people realized that the disease was not going to hit them. I mean,
yeah, I agree. But this is a sort of research that you have to do with no urgency, because the problem with COVID-19 was that, everyone rushed into modeling what was happening at the moment. And these sort of questions and this sort of modeling is the sort of things that we can do in academia when there is no ongoing disease or someone asking you, knocking your door, make a prediction of what will happen next week with this or with that. So it's something that you have to do in a more traditional way, that, think very carefully about your model, seeing what are the insights that they provide, etc. If you rush into it, you are, bound to failure.
Well, let me just say that part of my problem is a conversation that I had with a member of parliament who sits for a neighboring constituency in this area, who was making a speech in parliament about the failure of the mathematical modelers. And I questioned him, and to his credit, he called me back. But he is convinced that there is an emerging consensus that the mathematical modelers failed badly. So, so in some sense, there's a real question as to, where is the urgency? Because in that case, the kind of question that I'm asked now becomes suddenly a much more important question in order to try and engage with the politicians. Because if we don't engage with the politicians, then, a large section of them will believe that mathematical modeling is useless. And then they will go with what they think is common sense. And best guess is that that's a foolish thing to do, even when mathematicians are not completely accurate.
Yeah, I have not been in that particular situation because I am the university professor and director of my institute. I do research that is mostly basic research with some applications. But there I have some colleagues that have been, I have been in some task force, but at the early stage, etc. But I have some colleagues that they make a living out of, doing very precise models, etc. And they are also very frustrated because they have done a lot of predictions that at the end of the day have not been taken into account by politicians.
Okay, thanks very much. Anyway,
you're welcome.
Thank you. Yeah. I think it's been the success and influence of modeling, I think, varies quite a bit across the world. And I think locally, the community of modelers worked relatively well with the government. They didn't always get all the information they needed, and their advice was not always taken, but there was a lot of back and forth, and I think it was more
you remember one case, I don't remember where was it. I think it, well, I don't remember what the university in the US that they did a very precise model, very nice model, very accurate.
I think it might be University of Illinois.
It could be,
and
it failed. It fails because they model a lot of a scenario, a set one in which the students that were positive were not quarantined. And so the model failed, but just because it's a human, because they didn't take into account that people were, consciously escaping quarantine. And that's why.
But even there, you could argue it wasn't really a complete failure, because once it
was not a complete failure, of course, but
and what to crack down on.
Yeah,
and
but
that was
the
a case
reason
in which the state continued to consult them on their models. In fact, they
of course.
still continue to advise the state.
Yeah, the model is very nice. It's published in Physical Review X, I think, so it's very nice model.
Okay, were there any other questions? I think people have been waiting patiently.
Okay, thank you very much, everyone.
Thank you so much, Yamir.
Thank you so much. Yeah. This
Thank you so much.
And I look forward to meeting you in person one day.
Yeah, me too. Bye-bye. Thank you.
Bye. Thank you again.